In this video, we will learn about k-fold cross-validation, and we will take a look at the coding file directly. First of all, before we get started, let me ask one question. When a student is studying for a college entrance exam, who do you think has a higher chance of getting a high score on the exam? One student studies with the past exam questions and takes a mock test with those questions. The other student studies the past exam questions and then take a mock test with new questions that they haven't encountered before. Of course, the latter student, who performs well on the test with new questions, will have a higher chance of getting a good score on the college entrance exam. Furthermore, it would be much better to solve as many problems as possible rather than solving a small number of problems. Solving a greater number of problems can help achieve better grades. Similarly, just like in the case of studying for a college entrance exam, we can say that an artificial intelligence model performs well if it can make accurate predictions when presented with new data that it has never encountered during training. Therefore, as mentioned in the previous video, in the case of artificial intelligence models, the data is divided into training and testing data, and the model trained on the training data is evaluated using the testing data. Furthermore, just as solving a greater number of problems helps in obtaining higher scores, having a larger amount of data for training and testing an artificial intelligence model can result in better performance. However, in the field of food and life sciences, obtaining a large amount of data through actual experiments can be physically challenging. When the quantity of data is not sufficient, splitting the sample into large training and test sets is usually not feasible. If the quantity of data available for establish an artificial intelligence model is insufficient, you may consider using k-fold cross-validation. In k-fold cross-validation, the entire dataset is divided into k groups of equal size. For example, if k is 5 and the total dataset contains 100 samples, the data is divided into 5 groups of 20 samples each. First, the initial set of 20 samples is used as the testing data, while the remaining samples are used as the training data. Then, the second set of 20 samples is used as the testing data, with the remaining samples as the training data. This process is repeated 5 times, and the average of the 5 results is used as the final outcome. In this manner, k-fold cross-validation commonly uses a value of 5 for k. Next, let's take a look at the coding file with k-fold cross-validation. This time, we are going to apply k-fold cross-validation to a model that uses the support vector machine algorithm to classify iris flower data. The Jupyter Notebook file for this is available on GitHub, so you can download it and run it yourself. In addition to the necessary libraries like NumPy, Pandas, and TrainTestSplit, we also import min-max scaler for normalization. Then we import the SVC library and the k-fold library. We load the dataset from an Excel file and perform normalization. Using the shape command, we can examine the shape of the X and Y data imported from the Excel file, and we can see that both X and Y data consist of 150 samples. Next, we use the k-fold command to divide the entire dataset into groups. The number inside the parentheses represents k, and here we input 5 to divide the data into a total of 5 groups. Then, we create a support vector machine model with a linear kernel, a C value of 10, and a gamma value of 1, and store it in the variable svm. After that, we train the model using X training and Y training data and evaluate the accuracy for both the training and testing data. It's important to note that the 5 divided datasets need to be used as training and testing data in 5 iterations. This is achieved using a for command. If you want to learn about the detailed information on the for command, you can refer to the random forest video. Inside the for loop, we execute the print command to display the shape of the data and the accuracy at each iteration. As shown here, out of the total 150 data points, 120 are used as training data and 30 as testing data. We can also see that the process is repeated 5 times as shown 1, 2, 3, 4, 5, and we obtain the corresponding accuracy for each execution. Additionally, to calculate the average of the obtained accuracies from these 5 executions, we can do a simple calculation using Python coding. First, we create empty variables called train_list and test_list. We use the append command to store the accuracy results obtained from each execution in these variables. As a result, we obtain 5 accuracies from each iteration, as shown here. We can easily calculate the average of these 5 values using the np.mean command.